Today in topic 8.2 we're looking at transformations of log functions, and we're looking at how we can obtain y equals a log b of x minus h plus k from y is equal to the log of x through various transformations. Look at our parameters again and the transformations obtained. The parameter a is going to be a vertical stretch, so a times y for every coordinate. B is going to be x divided by b is going to be that shift. H is going to be a horizontal shift, so it's x plus h and y. And k is a vertical shift, where we have x and then y plus k. In example 1, we're going to use transformations to stretch the graph of y equals the log base 3 of x plus 9 plus 2. First of all, we're going to start with y equals the log base 3 of x, and we're going to compare some points. We know that 1, 0 is there. That's going to be a shift of 9 units to the left, so we're going to get negative 8, and it's going to be 2 units up, so it's going to be negative 8, 2. The next ordered pair, if we put a 3 in for the x, is going to be 1, and the log base 3 of 3 is going to be 1, so that's going to be a shift to negative 6, positive 3, and if we used 9, 2, we would get a shift to go to 0 and 4. And that's what that graph is going to look like, from the blue graph to the red graph. Now when we look at the domain of our new graph, we're going to have x is greater than or equal to, just greater than negative 9, not equal to. There's going to be an asymptote at negative 9. For the range, y is going to be any real number. There's going to be a y-intercept at positive 4. And to find the x-intercept, we're going to set y to equal 0, and we're going to solve for x. So 0 is going to equal log 3 of x plus 9 plus 2. Subtract 2 from both sides, and then take the log away from both sides, where we have 3 to the power of negative 2 is equal to x plus 9. Now we can say that subtracting 9 from both sides leaves us with 1/9 minus 9 equals x, or negative 80 over 9 is equal to x. In example 2, reflections, stretches, and transformations of log functions, we're going to use transformations to sketch the graph of y equals the negative log base 3 of x to x plus 6. Well, we're going to start out with y is equal to the log base 2 of x. Notice that we factored out the 2 from 2x plus 6 to get 2 times x plus 3. Now the first thing we're going to do from the log of 2x is we're going to make it the log of 2x. So every point is going to be divided by 2 along the x. Then the next point, well, that's what it's going to look like. The next, we're going to reflect it in the x-axis. So every point is going to be, for the y, is going to go to the negative. And that's going to be what the reflection is going to look like on that graph. And lastly, there's going to be a shift of 6 units to the left. So that's going to be 6 units, 3 units. Pardon me, because we've already factored out the 2. So we got negative 2.50, negative 2, negative 1, negative 1, negative 2, and 1, negative 3. We have an asymptote now at x equals negative 3. Our domain is going to be x is greater than negative 3. Our range, of course, is going to be any real number, as always. The y-intercept to set x equals 0 is going to be at negative 2.6. And for our x-intercept, we're going to set y to equal 0. And this time, you're going to divide each side by -1. We're going to take 2 to the power of 0 is equal to 2x plus 6, taking away the log of each side. So 1 is equal to 2x plus 6, -5 is equal to 2x, so x is equal to -5 over 2. In example 3, it asks us to determine the equation of a log function given its graph. Well, here it's important to look at a couple of key points. The red graph can be generated by stretching the blue graph of y equals log base 4 of x. Write the equation that describes the red graph. Well, notice that our blue graph is y equals the log base 4 of x. One of our points is going to be at 4 and at 1. But now the red graph is going to shift it, and it's like dividing it by a quarter. It's going, instead of going to be at 4, 1, it's only going to be at 1, 1. Therefore, we can notice that 4, 1 is a key point. It becomes 1, 1 in the stretched graph. And therefore, the horizontal shift is by a factor of 1/4. So the equation must be y equals the log base 4 of 4x. In our last example, with an application involving a log function, we say that welding is the most common way to permanently join metal parts together. Welders wear helmets fitted with a filter shade to protect their eyes from the intense light and radiation produced by a welding light. The filter shade number n is defined by that function, where T is the fraction of visible light that passes through the filter. Shade numbers range from 2 to 14, with a lens shade number of 14 allowing the least amount of light to pass through. The correct filter shade depends upon the type of welding, and a shade number 12 is suggested for arc welding. What fraction of visible light is passed through a filter of this filter of the welder as a percent to the nearest 10,000th? Well, since we're having a filter of 12, we're going to let n is equal to 12, and then we're going to solve for t. If we substitute, you're going to get 12 is equal to -7 over 3 times the log of t plus 1. Take away 1 from both sides, and you're going to get 11 is equal to -7 over 3 times log 10 of t. Now, since it was -7/3, we're going to multiply by the reciprocal, which is -3/7. And 11 times -3/7 is going to equal the log base 10 of t. That means that -33 over 7 is log base 10 of t. Now, 10 to the power of 33 over 7 has to equal t. And by evaluating that, I'm going to get t is approximately equal to -0.000019, and therefore a filter shade number 12 allows approximately 0.0019% of the visible light to pass through the filter. Our assignment then is based on this, and it is going to be page 389, numbers 1 to 10.